So we're going to start today with reviewing some of the big ideas from plate tectonics. And then we're going to finish with our notes about the evidence that we have that shows this theory is actually happening. So get a whiteboard and a marker, and we're just going to do like a practice quiz here. It's not worth any points. But these are things that we've already gone over and that you should know, but we probably didn't think about much in the last couple of weeks, huh? So we're going to do a little review quiz. All right. So all the questions are going to be about these diagrams up here on the screen. And the first question is basically, tell me what direction these plates are moving. You could answer this in two different ways. You could just draw arrows showing that they're moving apart or coming together, or you could just write down apart or together, right? So question one, in this diagram, which direction are the plates moving? If I was going to put arrows on here, where would I show them? What would I show them doing? Okay. Question two is, what is the name of that kind of boundary? What do we call this boundary when the plates are moving in that direction? Number three, that's all the labels, all the letters. Okay, so three is going to have, in this case, for this diagram, A, B, C, D, E through I. Question four is going to be an example. And the example has to have two things. First, for A, an actual feature somewhere in the world where this is happening. And B, you name the plates that have formed that feature by this process. Okay? So on your whiteboard, I'm going to wander around, just kind of look over your shoulder and say, perfect for number one, but try number two again, or whatever, okay? Try number two again. So far, so good. Which direction are they moving? You can just draw arrows if you want, or you can use words to describe the direction they move for number one. And number two, what do we call that boundary when they're moving like this? That's the right kind of answer, but it's not the right answer. So what direction are they moving? Number one and two are related. What direction are they moving? And then what's the vocabulary that describes that kind of movement? Okay? And then number three, you've got to go A through I, A, B, C, D, E, and name all those things. I noticed yesterday when I did this in class that people were using their plates map to help them. At least the questions had some of the stuff on it. It doesn't have those diagrams, but it talks about the names of the boundaries, and it talks about places where this happens. All right, 2 for 2 over here. Okay. What about number one? If we call it, yeah, just draw arrows showing the direction. Oops, that's backwards for number two. Just try. Oh, number one is good. Diverging is going apart, yeah. So far, so good. What's the vocabulary for that? And then for number 3, you got to go A through I. A, what are these? What do we call this whole layer here? From the dotted line all the way up. And try again. B is just this part. Call that layer. And then C, what is this above the dotted line? D, what's below the dotted line? And to help Kaylee out, I'm going to add one more letter on here. It goes like this. Do you see how this one is different than anything else?
That's the mantle.
That is the mantle. Letter J, yeah. Cover up there.
And then look at the.
You can look at whatever you want.
Oh, okay.
This is just a review, right? Good job on B. What is that short for? Letter C? Yeah, there you go. Okay, look at D. That's correct. But there is a vocabulary term I want you to give me there. That's why we separated into an upper and lower, because the lower has this vocabulary term describing it.
Is it?
What?
You're close. No, not anthro. That means human.
Just look at this thing. And then choose a plate that's.
Oh, yeah, you
slowly.
might want to fix that. Yeah. Joey found the perfect page to help him. The diagrams, so straight from that. Oh, yeah, Keely found it too. Huh?
Is it just lower mantle?
And there's a vocabulary I want you to give me for D. It is the lower mantle, but there's a vocabulary term. And it does start with A, and that's, I think you just wrote down the wrong thing on your notes. Yeah, it's kind of a weird word.
Anthro?
No, that's, so we talked about the anthrosphere when we did the 4 spheres. We added that as the 5th sphere, the sphere of people, which you talked about in your project. And I think you accidentally wrote that down here, and you should change it. It's not that. Okay? Well, let's see, E and I are both the same. Can you see that? E and I are both the same. You get one, you got the other. That's just crust. I need to know what kind of crust for E and I.
Oh, terrible. Oh, con. What's it? Continental? Continental.
The continents. The
Because
crust.
I wrote it wrong. I wrote it with an H, bro.
Yeah, you should correct some of those mistakes on there, so you studied the right thing. You're not trying to make up new words. You got litho what? Not outer core. Let's see. The crust that B is good. So in my 3rd period class, we've actually done this twice, this practice. One day, we had a snow day one day, I think, huh? We canceled school. You guys, but not for them. So in a way, they had an extra review. Upper what? It's the upper part of the mantle.
Under H.
Under H, H is this little asterisk, this star.
What's that thing?
G is a pair of wavy lines that look like this. That was my symbol.
Wait, but what's the under it?
What's under it?
Yeah, the H.
This
Yeah.
is the same as G.
Oh,
This is the same as H.
oh.
Okay? I think I showed you this rock before, right? Yeah? And this is the example rock from letter G. What did I call this? What did I say about this rock? What do I want you to notice about this?
Basalt.
That's letter G. What did I tell you about this rock? Okay, D is correct, but there's a vocabulary term I should have given. I don't like your number 4. Yeah, it's not a volcano. F is not a volcano. Looks like we need to practice some more, huh? So these diagrams are part of the test. The test would look just like this. Written part of the test. Right? Yeah? You finished?
No.
B is wrong. I is wrong. G is not wrong. F, try that again. H is good. 4 is wrong. Because what's the Nazca plate, you guys? The Nazca plate is ocean floor, isn't it? They are coming together, you're right. They are converging. But this is continent versus continent, so that's not Nazca. That would be continent versus ocean, yeah. H is an event. G is a thing. This would be a sample of G. No, there's no oceanic crust shown here. And this, let's go to G. What is this? It's a rock. But what's unique about this rock? Why do I keep holding it like this to show it to you? Instead of showing you the whole thing, I really want you to look at this end of it. Why is that? Yeah, we can see the layers, and what are the layers doing? Are they flat? Or have they been crushed? Have they been folded? Letter G, folded rocks. In this kind of a collision between plates, we compress these rocks and we fold them. So see how the wavy lines represent that? The folded rock. Okay? Now letter F is a mountain range, but wait, there are different kinds of mountain ranges. Some are volcanic, right? That's not this. The Sierras are not this either. The Sierras are what we call a fault block mountain range because the faults lifted the mountains up. That didn't happen here. Instead, imagine these plates colliding and they crumple up and force each other upwards. Can you imagine if this was like animated video? How they gradually grow bigger and bigger by compressing together? So this is a type of mountain range that we're going to call a folded mountain range. So letter F should be folded mountains. Letter F, folded mountains. Letter G, folded rocks. Those kind of go together, don't they? an event. It's something that would happen and it might scare you if it did.
Oh, no.
Yeah. When these are crushing together, we're gonna shake up the landscape a bit, aren't we? Yeah.
I heard of that.
Let's go over the answers first. What about number 4?
Isn't it just a folded mountain range?
I want you to name an example of a folded mountain range, an actual feature. And then you name the plates that are colliding together. Sam, you should look for this in your backpack if you think you did it. Yeah. Maybe you kept it because you were working on the questions on the back. Let's go over the answers. Number 1, what direction are these moving? They're moving together, right? You could write they're moving together, or you could draw arrows showing them go together. Number 2, what do we call that kind of boundary when the plates move together? Converging boundary. They're coming together, they are converging. Number 3A. Notice it has the crust and the upper part of the mantle. This is what we call the lithosphere. And this is what actually makes up a plate. The plate includes both the crust and the upper mantle. That's the lithosphere, letter A. So what's B? The crust. What's C? Upper mantle. What's D? The lower mantle, but I want you to include vocabulary for that, which is asthenosphere. So we have the lithosphere on top of the asthenosphere.
Is it good if you put lower?
If you put lower mantle, I'll only give you half credit. You need to know vocabulary too. Asthenosphere. Okay? So this is where the convection currents occur that carry the plates, huh? Because the plate is the lithosphere, the upper mantle is getting dragged along by the convection current underneath it in the asthenosphere. Letter E and I, in this case, they're both continental crust, huh? Do you remember what kind of rock makes up the continental crust? Granite makes up the continental crust, is granite.
Or basalt.
And no, basalt makes up the oceanic crust.
Oh, okay. That's
Okay, yeah. So you got to keep that in mind. Which is older, the oceanic or the continental crust?
Oceanic. I'm playing. It's granite by
Yeah.
3.5 billion.
Yeah, the continents are much older than the ocean floors. Because we're always making new ocean floor and we're always destroying old ocean floor. But the continents are pretty constant. Not their shape, because they break apart and they merge together. But they stay up on top of the crust. Whereas the ocean floor gets pushed down into the mantle and destroyed, huh? Or new ocean floor is formed by magma that rises up out of the mantle. So the ocean floors are much younger. Let's see, which one is more dense, ocean crust or continental crust?
The ocean crust.
Ocean crust is more dense, so which one goes underneath the other one when they crash into each other? Yeah, the ocean crust goes under because it's more dense. If you look at these two continents colliding, did one go underneath the other, or did they pretty much just merge together? They merged together, huh? And that takes us to letter F. When they merged, they formed that folded mountain range where the whole edge of the continent crumpled upward, where they crashed into each other. Kind of imagine two cars crashing into each other, and they get all crumpled up where they collided, huh? Letter G, the folded rock. Letter H, the earthquakes. We already did I. And J would be the mantle, huh? That leaves us with number 4, an example of where this happens. So for each of these different boundaries, you should keep one example in mind. The best example for this one is the tallest mountain range in the world. What's that? What are the tallest mountains? Mount Everest is the tallest mountain in the Himalayas.
That one in China. Oh, they're both in China.
Mount Everest is on the border between China and Nepal, I believe.
No.
Mount McKinley is not as tall, but, and it's in Alaska. But, so Mount Everest is the tallest of the entire mountain range of the Himalayas. And the Himalayas are from where what two plates collided with each other?
Continental plate.
You got to name the plates. Which plates collided to make the Himalayas? That's what it means when I say example. You have to name an exact place on the planet. When I say example, that's why we're saying the Himalayas or Mount Everest. And which plates? The Eurasian plate and the Indian plate or the Indo-Australian plate. Right? So if you look at your map, here's my map. Mine's cut in a weird place. India collided with Asia and forced those mountains up, making them the tallest mountains in the world today. See how that example works? You name the exact place and the exact plates that were involved. Good? Okay. Let's move on to our next image, which is this one. The same questions here, except this one also has a number 5. Number 5 is the process. So start by telling me what direction they're moving. Then name that, give me the vocabulary for that type of movement. Then label, in this case, A through G. Then give me a real example on the planet of where this is happening. And for this one, there's also a process that you need at the end.
Yeah, no, I was just trying to finish the label.
Even better. Going. That's right. I need to give you a hint about a couple of these. So as a hint for what I'm looking for, A and B, I want you to include the ages of these features. For A and B, how old is A versus how old is B? Because I've talked about it so many times. And then for E and F, you have to tell me something about the sediments. They're both about sediments, but there's something that is different between them that you got to tell me about. And actually, I'm recording this right now, and I'm going to post this video on Teams. Could you then quiz yourself on this to get ready for the test on your own time? Use this as a practice test. Oh, no, not you. Do you have those diagrams like these? that's what I'm basically quizzing you on, is these diagrams that we did a month ago. Right, keep going. Perfect so far. And if you have, how about you guys? Do you have these? Either of you have these with you? 'Cause this is what I'm quizzing you on right here, right? Anders? When we did this? Yeah. See, we did weird statements about that. Good. So I want to point out that this diagram is just a cross section. If you want a more three-dimensional view, look at this drawing I just put on the board.
Going up to G, right?
So there's the three-dimensional view of what we're talking about. It's not just a single mountain, is it? It stretches way into the distance. It's deep underwater, right? You can see the water at the top of the diagram. Okay, I'll be right there. Going on. I'll try to be easy. I want the age of those blocks. A and B were about the ages of the blocks. E and F are about the sevens. So E is good on try. C and D are excellent. G, I want you to tell me what's happening. It is the upper manifold. Guess which part of the convection current? Rising part or the falling part? The spreading out part? Try A again. I want to know about the ages of. See the dot, the red dot that I drew? I want to know how old that is compared to B.
Wait, what are you?
Try And then B is the same thing, but a different age. No, B. But C needed to be
The
changed.
plate and then.
So they're both oceanic crust, you just have to tell me about their ages. Okay? Try F again, I wanna know about the sediments there. D, you're on the right track, but there's another proper name for it, so I can only give you half credit for what you did there. Yeah, tell me about their ages, which is older, which is younger, air. Yeah, and then you never know the features at C and D. How is it in this corner? Struggling? Just a lot. Huh? Well, a lot of that stuff I posted videos. There's links on Teams. Just have to probably use it.
What did I? Oh,
Number 4. Oh, okay, those are good. Those are good examples of the plates. That's 4B. I haven't answered 4A.
features. Yeah, I know.
Yeah. So what is it that we find along that boundary?
Volcanoes.
Right. Well, what do we call this thing right through here?
Oh, what is it? The Mediterranean? No, it's, what is it called?
Maybe you have it.
Oh, the Ring of Fire.
No, not the Ring of Fire, but you're not far off though. That would be.
Oh,
an
the
example.
Primeuridium. That's it.
No.
Oh.
Should we go over them?
Yes.
Okay. So we got to practice, right? That's why we're doing this, because we got to practice. Practice makes perfect, as they say. So I know this is not, we're not ready to test on this. That's why we're practicing now, huh? So what direction are these moving? They are moving apart, right? So if I was going to draw an arrow here, if I was going to draw an arrow, I would do this, wouldn't I? They're moving apart. Let's see. I don't know what that is. I have no idea what happened with this little black box here. Anyway, let's just ignore it. If they're moving apart, what do we call that boundary? A diverging boundary, right? Diverge moves apart, converge moves together, yes? Number 3, labels. A, I want to know about the ages of these rocks. First of all, do you guys agree that this is ocean crust? Oceanic crust, made of basalt. But which is older, A or B? A is older, and I know Andres just told me why. Why do we know that A is older than B? Where is the new rock being formed? Right here, huh? We have new rock forming in there. So it's formed in the middle and then it spreads out to each side. So the further away it is, the older it is. Now tell me this. This is not one of the questions you had to answer, but it's something you should know. I want you to compare the age of A to the age of the rock over here at F. How does the rock right here, how does that age compare to this rock over here? I want to know about ages. I'm not answering any questions right now. I'm just asking this question, a new question. How does rock A, the age of rock A, compare to the age of rock F? They're the same age. Wait a minute. What about rock E? How does that compare to F? E is younger. Now compare E to B. They're the same age. Why? Because this kind of got messed up here, sorry. Because both these rocks got formed at the same time in the center at feature C, didn't they? They got formed at the same time, and then they got pulled apart. What about this? Here's two X's. How old are the rocks at those two X's compared to each other? They're the same age. But the X is younger than this, isn't it? But the X is older than that, huh? Okay, so keep that in mind. The rocks are formed in the middle, and then they get pulled apart. Right? That's going to help us with number 5, the process. What process is it that pulls them apart? So what did we do? We did the ages. Okay, C and D. What are these features? What is this thing that I've drawn and I've kind of shaded it in here? It's a rift valley. Rift Valley. At the top of this underwater mountain range. Kind of weird to have a valley at the top of a mountain. But that's what's going on here. A rift, if you don't know that word rift, it means a tear or a rip or a fracture. Sometimes we use it metaphorically to talk about people's relationships. Oh, there was a rift between Kaylee and Kevin. Okay? So a rift is when things get torn apart. Does that make sense that this is called a rift valley? Is the crust getting torn apart there? Right? The magma comes up, hardens into rock, and then moves off to each side. It's getting torn apart. It's a rift valley. Okay? And it's at the top of this underwater mountain range, letter D. What do we call that kind of mountain range? Not a folded mountain range, not a volcanic mountain range, not a fault block mountain range. Mid-ocean ridge. Yeah, this is a mid-ocean ridge. Now, sometimes it rises up high enough that it makes an island, like Iceland is part of the mid-ocean ridge. But for the most part, it's underwater. So C is the Rift Valley at the top of D, the mid-ocean ridge. E and F, what do we notice about the thickness of the sediments there? They're different. So which one, how would you describe letter E when I asked you to describe those sediments? Thin sediments, and F would be? Why? Because it's older. Sediments build up over time, don't they? As rivers come into the ocean, or for that matter, as creeks come into Tahoe, they drop off sediments. They drop off gravel and sand and silt. And those things settle to the bottom. When organisms die, their remains sink to the bottom and become part of the sediments. Sometimes they fossilize. Right? So the sediments build up over time. The older it is, the thicker the layer of sediments is, huh? Is that what we're seeing here? Do the old rocks match the thick sediments? Is it also true on the other side? Do the thin sediments match the young rocks? Right? So it's another way of measuring the ages of the rocks is by looking at how thick the sediments are. So that was E and F. Are we good with those? Thin sediments and thick sediments. Letter G, what's happening right here? Magma is rising up, and it actually lifts up the edges of the plates to make that mid-ocean ridge. Magma rising for letter G. Or you could say rising convection current would also be a good answer there. Are we good with all the labels? That takes us to an example. Again, for each of these, you should have one example in your brain. You could choose different examples, but I think you should just try to remember one. So this is a really good one to remember right here. It goes all the way from Iceland almost to Antarctica, huh? Between South America and Africa, between North America and Europe. Here's another good example over here, between the Pacific and the Nazca Plate. But this one might be easier. So what do we call this underwater mountain range? Specifically, it is a mid-ocean ridge, but which mid-ocean ridge is it? Simple, just name the ocean that it's in. The Mid-Atlantic Ridge. So for number 4A, one really good example is the Mid-Atlantic Ridge. Now name the plates that are moving apart. Which plates are moving apart there? The South American plate is moving apart from the African plate. Would it also be a correct answer to say the North American plate is moving away from the Eurasian plate? That would also be correct. You could make your choice, right? I recommend that you just choose to remember one of them. And I'll give you one more example if you want to make a different choice. Over here, where the Pacific plate is moving away from the South American plate, Pacific plate is moving away from the Nazca plate. That mid-ocean ridge is called the East Pacific Rise. That sounds like more things to remember, huh? Something new, the East Pacific Rise, the Nazca plate. You might have ever heard that word Nazca before. So it might be easier to stick with Africa, South America, and the Mid-Atlantic Ridge. We're good with that? Let's move on to the third of 4 diagrams. Here it is. I'm going to erase some stuff. Once again, number 1, tell what direction these plates are moving. Number 2, give me the vocabulary that describes that motion. Number 3, label the different letters that are on here. Number 4, give an example, a real place in the world where this is happening. And name the plates that are involved. And then number 5, oh, we didn't do number 5 on the last one. What was the process on the previous one where things are moving apart at a diverging boundary? What's happening to the size of the ocean over time? It's getting bigger. So what do we call that process? Oh, no. Give you a hint, SFS. Seafloor spreading. That was what was happening here. This is seafloor spreading for number 5. Forgot to go over that with you on the answers. That's the process that occurs here, seafloor spreading. Good job. So let's go ahead and do the third diagram. Here it is. Same 5 questions. I put a dotted line around letter D because it's that old D. Kevin, let's do geology right now, okay?
Direction is down. That's like that.
Did you guys see that some people's projects are posted on the wall in the hall there? People that made posters. Hers is.
Mine?
Did you make a poster?
Yeah.
Did you put your name on the back?
Yeah.
I think, did you do Hawaii?
Yeah.
Yeah, it's right here. It looks very nice. So first of all, I want to celebrate that those guys did their work and did such a nice job on it. Secondly, I want to remind you guys every time you walk through there that maybe you didn't do that project and you better. We're running out of time.
Yeah, that's fine.
Projects are worth a lot of points. And you have one more project ahead of you. Yeah, in fact, after today, most of the rest of class for the semester is going to be devoted to working on that project.
have to be turned, or like, when's the last day?
The last day to turn stuff in is, I have to look at the calendar, the week before finals.
Oh,
Next, is this
the
next
next
Next Friday.
I gotta wait.
Like a
I bet.
final project?
What's
Or
that?
on next, is it gonna be like a final project?
Well, it's a unit project for this unit, but it's a big one. It's about earthquakes. It's a two-part project. One part is about earthquakes.
It's
The
bigger
other
than
part
last
is
one.
about volcanoes. I think it's a little bigger than the last one. Yeah. Earthquakes and volcanoes.
Which one is the magma rising
What
beer?
is it?
Oh. B. And then A, I didn't really draw the feature because it's too obvious what it is once I draw it.
Yeah. Okay, what is it? Yeah. I was like, I
I
know.
thought it was just, the type of basketball skills you have. Be careful on this one. There are three types of boundaries, right? Three types of boundaries, but we have four diagrams. Doesn't that mean we have to use one of the same boundaries twice? Indeed, it does. It's not transformed. I'll try number two again. You're not wrong,
No, I was
okay?
wrong.
And I'll tell you, number two is a process. So number two,
Yeah.
yes, and what do I ask for on question five?
Oh, that's the process.
Yes, so number two is the name of this boundary. Oh, we're supposed to put up here at the top of each one. Is the name of the boundary. But you already know, because if they're coming together, what kind of boundary is it? Yeah. Okay, you're doing great. I would like
No,
to
they're
change this
together.
last word here to melted. Put F and H. Really, this is. Yeah,
But that side's not.
well, maybe it's backwards, but, okay. Good, now it's H. Keep going through it. Okay. It's too easy for you, Gabby, that's why you're not able to figure it out.
Water.
So what's H?
Oceanic
It's,
crust.
no, H is not the oceanic crust,
Just water.
Mid-ocean?
it's just the ocean. It's just the ocean, right? Just to make sure that we're all clear, when I say oceanic crust, I'm not talking about the ocean. I'm talking about the ocean floor, right? The rock below the ocean. And that's why I labeled H on there. And it's so obvious and simple that we sometimes can't even think of it, huh?
Is C where the person,
Yes.
and what's J?
Conversion and then I.
There is no J.
Subduction.
Oh, I thought that was J.
No, this little thing right
Yeah,
here,
I thought that was J.
no, that's not a J. That's just some of the crust melting.
There's no I, how can there be a J?
I could have mislabeled.
Yeah.
No, but can you do another alphabet?
It wouldn't be the first time I made a mistake.
Oh,
Do you know your Greek alphabet yet?
I know
I don't even know.
You know
that.
Delta. You know Omicron. From last year, you know Lambda,
Alpha,
We have to wear.
Alpha,
beta.
Beta, Gamma,
Oh, did you know that?
Delta.
We have to wear again.
Except the word girl.
All day in class, and I'm supposed to let them know if you're not.
Thank you for your service.
Perfect.
For stepping the Without Kevin. Dude, if I saw Katie on the battlefield, bro, I'd just quit, bro. I just forfeit, bro. USA is over, bro. Just because of KD, bro.
Try G again. That's just what kind of crust is it? Same with F, just name the types of crust. Right, it's like a long underwater valley. but it's a specific name. Nope. And you did F. What would you do for G then? Not G. G is this whole thing. Right? Oops. Am I right?
And would
Okay, so
F be
these things are moving together. It's like this. Here's the one, letter G, and then letter
oceanic?
F. So they're moving together. What do we call that when they come together? Sorry? Close.
Deep trench.
It was the same thing as number one. It was two continents that collided. And we did this, right?
Hawaii
This is now ocean floor. Underneath them.
Big brace off blue.
What is it when they come together? What is it when they move apart? They both end with urging. That's why you said merging. Diverging. Converging. There are many examples you could name of this. You just should remember one of them.
Hawaii volcano.
Not Hawaii. Sorry. Hawaii is a unique situation. It's in the middle of a plate instead of on the boundary of a plate. So,
Is it just a volcano?
Hawaii? Oh, which one?
A.
Yeah, I didn't draw letter A really because it's too obvious once I draw it. If I was gonna draw it,
It's a Hawaii volcano.
no, it is not a Hawaii volcano.
And what you get for D?
If I was gonna draw A, it would be something like this.
What did you put up? Volcano across for A?
That's perfect.
And then. How did you-
D. No, that's not what I'm looking for. That's what it is, but this place that I circled with the dotted line has a name. This region, this location.
Hey Kevin, when did you work?
Yeah, you want to try D again. You're right, that's what's happening, but there's a name for this.
What time? 3? 3 to 7 or what?
All right, let's
Oh, is it
draw. Okay.
current?
No. Let's go over the answers. So number one, once again, these plates are coming together, huh? But instead of being two equal plates that crumple up and form that folded mountain range, the denser one gets pushed underneath, huh? But they're still coming together. So it's still, number two, a converging boundary. Okay, we have two different kinds of converging boundaries. We have two continents collide, which we already did, and now we have a continent colliding with the sea floor. So number one, coming together. Number two, converging boundary. Number three, A, well, now it should be easy that I drew it. That's a volcano, right? 3B, what's this stuff? And what's it doing? This is blobs of magma rising up to the volcano, huh? So letter B, magma rising. Letter C, what's happening down here? The ocean crust is melting. Letter D, where the ocean crust is pushed underneath the continent, we call this the subduction zone. So a zone is a place, right? So this is the place where the crust is subducted. Letter D, subduction zone. Letter E, where that ocean floor gets pushed underneath the continent, it gets very deep, but it's also long and narrow. It's a deep sea trench. Deepest places in the world are these deep sea trenches. Anybody know the deepest part of the ocean? The Marianas Trench is a deep sea trench where the Pacific floor is getting pushed underneath the, I believe, the Philippine plate. Oh, yes. Mount Everest is 5 miles above the sea. The bottom of Marianas Trench is 7 miles below the sea.
It's 2 miles.
To still have 2 miles of ocean if you dropped Everest into the Marianas Trench. That's how deep it is.
Where's this?
It's near the Philippines.
That'd be scary, like you're swimming. And then you go into a trench.
You know that guy, he's a movie producer, James Cameron, I think. I think he did Titanic and he did Avatar. And he actually took a trip to the bottom of the Marianas Trench because he's so interested in the ocean.
And then you die.
No. He didn't swim, he was inside a sub. That was specially designed to withstand the pressure of 7 miles of water stacked on top of your head. Yeah. And you can feel your ears getting pressure just at 10 feet, huh? I don't know. Let's move on.
At the bottom of the pool, my head.
Yeah.
How did they do 7 miles?
Yeah, they got to build the, they got to design it to withstand the pressure. F equals ma, right? F equals ma. They got to calculate that into it.
How do people even go like 100 feet down with like snorkel gear on? Because my ears, bro.
Yeah. Well, you have to learn how to balance the pressure. One way is to hold your nose and then blow, which builds pressure inside of your ears and balances the pressure outside. Yeah, a diving bell. That way your ears don't have to withstand the pressure. Or a diving spear. At any rate, that was letter E, the deep sea trench. Letter F and G, all you have to do there is name the type of crust. So F is the oceanic crust and G is the continental crust. Letter H is just the ocean. That takes us to examples. Again, there are several examples you could choose in places on Earth where this happens. Just remember one of them. One good example is Japan. And the plates involved would be the Pacific plate getting pushed underneath the Eurasian plate, making the volcanic islands of Japan. Another example that you could choose would be the Andes Mountains of South America, where the South American plate is getting pushed underneath the Nazca plate. Another example, if you want to think about Alaska, is the Aleutian Islands, where the Pacific plate is once again getting pushed underneath the Eurasian plate. And you should just choose one of these examples to remember. Which one will stick in your brain the best? Another one, the closest example, is the Cascade Mountains, like Mount St. Helens, Mount Rainier, Mount Lassen, Mount Shasta. Cascade Mountains, where I went skiing over the holiday in Oregon at Mount Bachelor. These volcanoes are all formed where the North American plate is going over the Juan de Fuca plate. So have you chosen one of those to remember? Or do you have a different example to remember? Anybody? Which one did you choose? Tell your neighbor. Which one are you going to remember? We had Japan, we had Mount Shasta, we had the Andes Mountains, we had the Aleutian Islands. Okay, and what process is this, you guys? Subduction. Right? All right, last one. is. This one, there is no process to name. Just give me the direction of movement. Tell me the vocabulary for that type of boundary when they're moving in that direction. Label A, B, C, D. And then give me an example of a specific place in the world where this is happening.
United States.
Right, Gavin?
I even labeled it.
Didn't label it.
I don't think you guys labeled anything.
We didn't do this one?
No.
Well, we did, but we didn't label it.
We didn't label like the.
Like C's earthquake, but that's it, bro. That's all I know.
Okay, yeah.
Yes, right?
Isn't it just a plate
So-
and a plate earthquake and then B's like the ridges
Where does the earthquake happen?
at C?
Where do earthquakes happen? On a
Ridge.
on a fault.
On a fault.
B is a fault.
And then A and B are just crust.
It could be any kind of crust. It could be ocean and ocean. It could be continent and continent. It could be continent and ocean.
What do we call it? We just put.
Can we put any crust?
Yeah, you could put any crust.
And then C's that one's earthquake.
Except
right?
pizza crust. That one doesn't work.
And then D's also any crust, right?
Yes. Then name a place and name the plates that are involved. So this was the third kind of motion, right? Did you get that one? Like Kevin did. You didn't answer number 2. That was 1 and 2 over here. Try 2 again. You got 1 and 2. Good. Which plates involved then, Kevin? Oops, they're not coming together. Look at the diagram. See how I drew this one kind of 3D?
San Andreas
So you
fault.
can see that one's moving towards you, the other's moving away from you. So one arrow goes up and one arrow goes down. And this one's kind of a weird name. This one called a transform boundary.
No, North America.
As if it's changing, it's transforming. All right, number 1, they're moving in opposite directions. One's going up, one's going down, right? One's going forward, one's going backward. One's going east, one's going west. And we call that what kind of boundary? The transform boundary. So number 2, transform boundary. When they're sliding past each other, that would be another way to describe their direction. If you didn't want to draw arrows, you could say sliding past each other. At a transform boundary, number 2. 3A and D are both any kind of crust. You could put oceanic, you could put continental. I don't know about pizza. B is the fault, and C are the earthquakes that occur when these slide past each other. And our best example for number 4 is the North American plate and the Pacific plate. That would be 4B.
The specific.
And 4A, what feature is actually there? You guys were saying it before. What fault is it? San Andreas Fault. So 4A, San Andreas Fault. 4B, North American plate is moving past the Pacific plate. Are we good? So practice with that. At this point, we're going to finish what we started on the evidence for plate tectonics. So please erase your boards, put them away, and get out that evidence for plate tectonics assignment. get this ready to go first? All right, so evidence for plate tectonics. I wanted you to complete a set of guided notes, right? And we should have done the first half already before break. And the reason it makes sense to divide this in half is because we have two different theories to think about. The first one, the older one, the original theory, developed by Alfred Wegener, is continental drift. So Wegener came up with this idea that the continents could move, and he called it continental drift. And his ideas were not accepted right away. But then, about 50 years ago, we gathered a bunch of new evidence that supported his ideas, but expanded beyond them. So what I want you to think about is that continental drift and plate tectonics are basically the same thing. But continental drift is the older, incomplete version of the theory, and plate tectonics is the modern, more inclusive version of the theory. Continental drift left out the ocean floors, but plate tectonics includes them. Continental drift, we didn't know why the continents were moving. We didn't know how they could move, what force would be strong enough to move them. But with plate tectonics, we're pretty sure that it's the convection currents in the mantle that are moving them. So we should have already finished this page. We should have already finished page 2. This is all about continental drift, the older theory. And that takes us to page 3, the more modern theory that we call plate tectonics. And so that's where we're going to pick it up. So what evidence is there for plate tectonics? Well, first of all, I just want to point out that a good theory can usually be described in just a short phrase. And we'll see that phrase down here at the very bottom. The last bullet says that the Earth's crust is broken into pieces that move. That's a very simple description of plate tectonics, but it pretty much says the whole thing. Earth's crust is broken into pieces that move. Boom. And we measured how fast they moved in a different lab the other day, right? Before we left. We calculated the speed of plate movement. So the whole idea of the theory is that Earth's crust is broken into pieces that we call plates, and that these plates move. The word tectonics means to build. As a result of these movements, we build mountain range. We build volcanoes. We build deposits of gold, all as a result of plate tectonics. So we're going to look at a series of slides that present evidence gathered since the 60s showing that these plates move. Each slide will summarize a category of evidence that Wegener did not know about. His ideas have not been tossed out. They've just been improved upon. We've added to them. We think his ideas were incomplete. He didn't have all the data. So he didn't have a complete theory because he just didn't know it all. We didn't have the technology. I don't think you have to write anything from this slide, by the way. This new evidence expands on Wegener's ideas by including the sea floor, and it also includes a force that's powerful enough to move the plates. Keep in mind, each category of evidence is supported by many individual facts. Okay? Are we ready? So what is this new evidence? Where does it come from? Well, we have 3 main categories of new evidence. First, we have sonar. Second, we have something called a magnetometer. And third, we have these deep sea drilling rigs where we can drill into the sea floor. So the big breakthrough for Wegener's ideas came in the 60s when we developed this new technology used by oceanographers to map the sea floor. This technology included sonar, magnetometers, and deep sea drilling apparatus. Are you with me? I think at the top of that page 3, it asks you what the 3 types of technology are. Is that right? Okay. And the new technology gave us information about the seafloor that was best explained by the concept, once again, that Earth's crust is broken into pieces that move. In other words, plate tectonics describes what we discovered pretty effectively. We're good? Okay, so we're going to talk about sonar. Then we'll talk about the magnetometer, the magnetic data, and then we'll talk about what we found from drilling into the seafloor. So let's start by talking about how sonar works. Sonar is also known as echolocation, and we find an object by its echo, by using sound to find the distance to an object. The same approach is used by some animals, like dolphins and bats, use echolocation to find their food or to find their way around in the dark. So the first thing that happens is we create a sound. And in this diagram, it's shown with these pink waves going down from the ship. So you're describing the steps of how sonar works, right? On your notes. First thing, we create a sound pulse. Next, the sound bounces off an object. In this case, it's the seafloor. For a bat, it might be a tree, or it might be a moth. For a dolphin, it might be a fish, and they can tell how far away that fish is. Third, the echo returns to the ship, or to the bat, or to the dolphin's ears. And that's shown in this diagram with the green sound waves bouncing back. Next, we measure the time it takes between making the sound and the echo to return to us. What do you think? The further away it is, yeah, but in terms of time for the echo to get back, if it's further away, how long does it take? If it's something close to me, how long does it take for the echo to get back to me? If it's something far away from me, how long does it take for the echo to get back? It takes longer, right? So the further away it is, the more time it takes for the echo to get back to the ship or to get back to the dolphin's ears. This is why some bats have really big ears, right? And then their brains are able to calculate that time. They don't think about it. They're not putting a number on it, but they're responding to it, aren't they? If an echo bounced back to them really fast, they'd know that they'd have to swerve to avoid an object, huh? Less time means the object is closer, more time means the object is further away. And then with really fast computers, like in the second diagram here, a ship can send down multiple sonar beams at once. It can have multiple echoes measured at the same time. And see how some of these go off to the side? So we call this side scanning sonar. And this allows you to map a whole big zone of the seafloor at once instead of just one little point at a time. But you have to have fast computers to do that, don't you? Oh, yeah, we're not done with texting or whatever's going on. Doesn't seem to be related. Are we good with that one? You described how sonar works? Let's move on to what we found. So here's an example that's close to home of Lake Tahoe, where we've used sonar to map the bottom of the lake. And this process of making a map of the bottom of a lake or the ocean floor is called bathymetry. Bathy means deep or depth, and Whenever you have meter or metry, it means to measure. So what is mapping the seafloor? It's measuring the depth, isn't it? It's bathymetry, measuring the depth of something in order to make a map of it. Once we can see the shape of the ground underneath a body of water, we can start to ask questions, and then we can look for answers. So look at this map of Lake Tahoe. What I want you to notice is these hills down here. You see these hills in the middle of the lake? The purple is the deepest water, right? And there's these hills that are blue in the middle of the lake. Where did they come from? How did they get there? How were they formed? We know they're there. We've measured them. It leads to this question, how did they get there? So, look at those hills. There they are right there. I don't know, did you see that? Or they got circled? That should probably be a different color so it shows up better. Well, what we next noticed was over here we have this big bay. And you've probably driven over on the west shore. This is called McKinney Bay. But do you see how it's pretty much shallower than the rest of the lake? Almost like it's a separate part of the lake, huh? And you also notice that it's all kind of crumpled up over there. This is McKinney Bay. Well, it turns out that there is also a fault going right along here called the West Tahoe Fault. So these are things we know to be true, right? There are underwater mountains. There is a bay over here, which is shallower than the rest of the lake. And there's a fault line along that side of the lake. Now let's put all that together. Well, let's look. Here's McKinney Bay and the fault line. The yellow line is the fault. Here's the bay over here. Does it kind of look like that bay caved in on itself? And you see that it kind of looks like a bunch of this stuff crumbled down? Well, we think that's what made those hills. We think that there was a big earthquake on that fault line, and it caused an underwater landslide from McKinney Bay. And those mountains that we see over here are debris from that landslide. And these are like a mile in size, maybe 500 feet tall. So we think that these hills were once up here, and then an earthquake caused this whole side of the lake to collapse. So first an earthquake, then an underwater landslide. But wait a minute, if there's all that ground moving underneath the lake, what's that going to do to the water at the surface? Yeah, it's going to make a tidal wave, right? And wait a minute, the lake is kind of small. So what happens when the tidal wave hits one side of the lake? It bounces back, and then it hits the other side and bounces back again and again and again. And we have a name for that. We call them Seiche waves. It's kind of like, you've probably seen it in a bathtub. Like you sit down in the bathtub and you make a big wave that hits one side and it comes back and bounces back and forth, huh? Lake Tahoe is kind of a big version of that. We don't think, like, if this happened right now, we don't think that the tidal wave would be big enough to hit us here at the school, but it would probably hit the Hyatt. It'd be like 5 or 10 feet wave coming in all at once. Lone Eagle Grill, the beach down there, right? The lakeshore houses might be in trouble. Uh-huh. Yeah.
All the insurances, bro.
Yeah. But do they have earthquake insurance? If they don't have earthquake insurance, they might not get any coverage. Okay, so this is some of the information that we've discovered from bathymetry studying Lake Tahoe, huh? We can get more information about the ocean floor by mapping the entire ocean floor. And so this is what we come up with. So this is where it says evidence for plate tectonics 1, maps of the seafloor. You should summarize some stuff from this slide. So we've made these sonar maps of the seafloor, and it was a little bit of a surprise. we thought that the ocean floor was a flat, featureless plain with no hills, just this flat plain going from one continent to another. But then we actually mapped the ocean floor and we found all kinds of features. We found mountains, we found valleys, we found trenches. Sonar maps showed that there's a series of underwater mountain ranges circling the globe, shown in red in this diagram, kind of like the seams of a baseball. These are actually the longest mountain range in the world, and we call them the mid-ocean ridges. We didn't realize it at first when we discovered them, but now we know that the ridges are the edges of plates. So focus on the evidence when you're writing things down. What do we know for sure? Well, we know for sure that there's these underwater mountains that we didn't know about before, huh? Because they were underwater. We discovered the mid-ocean ridges because of sonar. Wegener didn't know about that. He didn't have sonar. Might be one of the reasons he left the ocean floors out of his theory. What I think is really interesting too, you know how Africa and South America fit together pretty well? Doesn't the mid-ocean ridge have that same shape? Once again, confirming these ideas that they were once connected, huh? This is kind of like the scar from where they were once joined together. By itself, that seems like kind of a weak piece of evidence to me. We'll see some strong evidence coming up.
Wait, Mr. Burton,
Yeah.
can you possibly go back to the last slide? I didn't realize we had a break.
I don't think you had to, oh, you only had to define bathymetry was the only thing, right? Okay. I think this is the picture you have on your notes, isn't it?
Yeah.
And can you see the mid-ocean ridges there?
Yeah.
Right? Here's the East Pacific Rise. Here's the Mid-Atlantic Ridge. So we mapped the seafloor and discovered all kinds of surprising things. All right, paleomagnetism. Okay, paleo, what does that mean? Paleo. You might have heard of paleontology, one of my favorite studies. Paleontology is fossils. Yeah. Ancient life. A paleo diet. Have you heard of that? That's when people think, oh, I'm going to be healthiest if I eat a diet like a caveman. The ancient diet. Paleo diet. Paleomagnetism means ancient magnetism. So, here it is. There's your definition. Ancient magnetism. So we can use this device called a magnetometer. Again, it has meter in there, which means we're measuring something, huh? Magnetometer to measure the magnetism in rocks, like this one. We can measure the magnetism in this rock. And here's how it works. Volcano, the lava that's erupted from the volcano, which turns into a rock like this one, this particular type of rock, basalt, has iron crystals in it. And you know, iron is attracted by magnetism, isn't it? And it turns out that these crystals of iron are kind of like long needles. So I'm going to use this pen to represent a needle of iron crystal inside this rock. Right? Now, when the volcano first erupted and the lava flowed down the side, it was all liquid, wasn't it? And that means that these iron crystals were all pointing in random directions. I think this is where you're supposed to describe how paleomagnetism works, right?
Yeah.
At first, when the lava is liquid, the iron crystals are pointing in random directions and it's flowing down the mountain and they're tumbling over each other because it's a liquid, right? But as it cools off, but not before it's completely solid, as it stops flowing downhill, that gives those iron crystals a minute to point north because they act like a magnet inside the lava. And then the lava finishes cooling, completely hardens, And now those iron crystals are fixed in position. They're frozen in place. And if we look at an old rock, we can figure out what direction north was when the rock was formed. So that's why we call it paleomagnetism. Good with that? Okay. So, what have we discovered? Well, you take a ship with a magnetometer on it. It's inside this thing they call a towfish, and we measure the magnetic fields of the rocks. And this is what we discovered. It's crazy that the magnetic fields in these rocks don't always point north anymore. When the rock formed, it must have pointed north, but now it doesn't point north. So either the North Pole moved, or the rock that forms the sea floor moved. That's what we discovered from this. So this is evidence number 2, I think, on your notes. It says evidence for plate tectonics 2. The magnetic field of these rocks doesn't point north anymore, which means that the plate must have moved. With me? Like north is about there, I think. But I measure the magnetic field of the rocks underneath the school, and they're pointing over there. Doesn't that mean we probably moved those rocks? Yeah. So the rock must have moved since the lava hardened. That's the big idea. The magnetic field doesn't point north, which means that the rock must have moved. How would it move? By plate tectonics. Convection currents carrying the sea floor around. We good? Okay. Next. That's just the tip of the iceberg, the fact that they don't point north. The really crazy thing is that sometimes they point completely south. They point the wrong way. What's going on? We call it magnetic reversals. Okay, is that evidence number 3? Mirror image. Explain what happens during a magnetic reversal. That's where we are now. We're talking about the magnetic reversals. Look at this graph down here. Look at the red line. You see how sometimes it goes up and sometimes it goes down? If it's pointing up, that means that the magnetic iron minerals are pointing to the North Pole. If it goes down, they're pointing at the South Pole. Can you see that the magnetic north and south have flipped multiple times? So not only do magnetic fields sometimes point away from north, but they also completely flip from north to south, then back to north, then back south, then north again. Not sure exactly why or how this happens, but we do know that it does happen. We call it a magnetic pole reversal. Apparently, the north and south magnetic poles switch over time. Magnetic north is towards the Arctic for several thousand years. Then, for a couple thousand years, magnetic north is now towards Antarctica. And then it flips and points to the North Pole again. Then it flips and, wait, I'm all confused. I'm talking about the magnetic pole, huh? So when I'm talking about pole reversals, I am not talking about doing this. This is not what we're talking about, is it? This is still spinning along here, right? And up is up. But your compass points up here today. But 10,000 years ago, your compass would have pointed down here. 15,000 years ago, it would have been pointing up here. 30,000 years ago, it flipped down here again. We're not sure exactly why this magnetic compass flips from north to south. And it does it kind of randomly. But it happens. We can measure it. So we have this complete flip of the magnetic field. We're not sure how or why, but we can map them across the seafloor. And this is really powerful evidence for seafloor spreading. So here we go. You have this diagram on yours, right? Look at the little plus and minus signs. Where it's gray and there's a plus sign, that means the magnetic field points north. Where it's white and it's a minus sign, that means the magnetic field points south. Now stop for a second and just analyze this diagram. Please look over here. How many plus signs do I have? See those three together there? Look on the opposite side. What about right next to it? What about right next to that one? What about here in the middle? Are these mirror images of each other? Starting at the mid-ocean ridge, we have a mirror image. Does that support the idea that the rocks were formed together and then dragged apart? And then a new set of rocks was formed with a minus sign, and they were dragged apart. And then a new set with a plus sign because the magnetic field flipped, dragged apart. Right? So go ahead and describe the mirror image of these magnetic field reversals.
This part,
I think this is evidence 3, mirror image magnetic field reversals. You have this same diagram. So if we look at a map of these polarity reversals, we find this mirror image of the polarity patterns on both sides of the mid-ocean ridge. This suggests that the lava hardened at the mid-ocean ridge, and that recorded the direction of magnetic north at the moment that the rock was formed. But then the rocks were moved off to either side of the ridge. New lava formed, hardened, recorded the new magnetic field direction, and then got torn apart and took it in the opposite direction. And this gave us this idea that the ocean floor is being formed here and moving apart in the process called seafloor spreading. Here's a really nice diagram of it, but a little bit harder to analyze. Look at this one. Look at this guy. This is the oldest, letter A. And can you see how these kind of orange-brown rocks were formed at the mid-ocean ridge? Then look at letter B. They're still there, but they've been moved apart. And we get a darker orange rock being formed, huh? Then those get pulled apart, don't they? And we have this new red rock being formed. Does this describe what we've been talking about with the plates being pulled apart at a diverging boundary? Right? Really powerful evidence for plate tectonics. And it looks like we have to come back to this next time, huh? So let's see. What do you need to do? Yeah, you might need to catch up on some stuff. Get ready for the new project. See you later.